thank you to the organizers for this great meeting. It's a real pleasure to be here and to be taking the place of Andreas, who graciously sent me instead. So it's great to meet all of you here. So the title of my talk is Quantum Magnetism of Iron Atoms on a Surface. And we're going to be talking about the iron on MgO on silver system that Suzanne introduced to us. And thereby, the first part of my outline has already been done, which is great. So we can jump into, so we've already looked at what are the states of this thing and the spin excitation spectroscopy that informs this. So we're going to jump into the dynamics of the system. So what's the spin relaxation time of the excited state? And then we'll move into another principal parameter of a spin system, which is the T2 time and how to control this thing coherently in spin resonance. Okay, so on the left, we have a surface of silver with 1, 2, and 3 monolayers of MgO labeled 1, 2, and 3, and there's single iron atoms deposited at low temperature on this. And so this is a single atom spin on an ultra-thin insulator. And the question is, what's its lifetime? So we know that iron atoms on bare metals will have hundreds of femtoseconds to picoseconds of lifetime. So how good is a 1 monolayer insulator? And what's the benefit for going to thicker insulators with the STM? So the tool we use to read out the lifetime or the magnetic state is a spin polarized tip. And so we make these by terminating the apex of a metallic tip that's typically terminating in silver with an iron atom. And this makes the tunnel junction magnetoresistive. So we measure a larger conductance when the spin on the surface and the spin on the tip are parallel or aligned versus when they're anti-aligned. And so under an applied magnetic field, the states of iron split, the ground state 0 and 1 split. And so we end up with a ground state 0 and an excited state 1. And under a special set of parameters, the lifetime is actually rather long. And we can see the switching of this iron atom in 2-state noise on an oscilloscope in real time. So this is a 1-second trace. And we see that at these conditions of 7.5 picoamps at 10 millivolts at 5 Tesla, we can actually read out the states directly. And this is a bit of a special set of parameters because we'll talk about the tip distance dependence of the lifetime. And 2-state noise is not necessarily useful under all conditions, because if we go to lower and lower currents, we can't actually discern these 2 states. And if we bring the tip too close in, the bandwidth speeds up, and so we can't read out the states. So let's talk about pump probe spectroscopy, because that's what we'll move on to for characterizing the T1. So I mentioned we have the same splitting between the 2 ground states. So we have a delta E between them. This makes state 1 metastable and state 0 stable. So we're looking at this dynamics of relaxation out of the 1 state to the 0 state. And so at thermal equilibrium, these delta E's are much larger than kT. We're working at half a Kelvin. Delta E is about a millivolt. And so at thermal equilibrium, essentially, we're only populating the 0 state. So I'll add these population indicators on the various states, and we'll look through how. Let's see what we do during this pump probe measurement to measure the relaxation out of the 1 state. So the first thing we have to do is actually populate the 1 state. So we do that by applying a large enough bias voltage such that we can do these inelastic transitions between the states. So this effectively distributes the population, time average population, to all states. When the pump is turned off, the upper states quickly decay into the lower 2. And now our task is to determine what the lifetime of this excited state is. So the way that we do this is we're inquiring what the population is at a certain time delay after pumping the system through the excited state. And we already mentioned that we can read out the magnetic state using the spin polarized tip. And so we let the system decay, and at a certain time we strobe the system with a probe pulse that's low enough to not excite the system, and we just do this readout at a specific time delay. So we can get the lifetime at various tip sample distances. And so we have three decay curves here of the excited state. So the question is, what is the lifetime of iron on MgO if we measure an order of magnitude change in lifetimes with only about a 1.2 angstroms change in tip height? So let's plot these lifetimes as a function of the tunnel current. And so we vary the tunnel current and plot it on a log plot. And this is just another way of saying tip height. So 1 decade in tunnel current is approximately 1 angstrom. Here's some calibrated scale bars. And along the bottom axis, we're plotting tip sample conductance in Siemens. And so 10 to the minus 9 just means 10 to the 9 ohms. So that's a giga-ohm sample impedance. So this is lifetimes for iron on 1 monolayer of MgO. And you see that there's a very strong tip dependence when the tip is close from the atom. But then it plateaus to a value that's independent of the tip proximity when the tip is far, and that plateaus at 2 or 3 milliseconds at this given field. So what's going on as a function of tip height? So we'll spare a bit of the details and get to this model, which is we have an iron atom that's tunnel coupled to some nearby electrodes. And essentially we can explain the scaling of the lifetime due to the conductances between the various electrodes. So this is electronic de-excitation from scattering between the tip and the surface. So the rate out of the excited state, which is just 1 over the lifetime of the excited state, is proportional to these various conductances. The first one is a constant of the surface itself, so that's sample to sample scattering. And that gives us a substrate limited lifetime. This is our plateau value, which we take as intrinsic to iron on this surface. And then we have a portion that's proportional to the tip sample conductance, and that gives us a part which is only necessary to include intermediate tip sample heights. And then finally, we have tunneling from the tip to the tip, which dominates, and this actually scales as the square of the tip sample conductance, and that's because it's 2 trips through this tunnel barrier. And that gives us a slope of a slope of 2 on this log-log plot of T1 versus tip sample conductance. So it looks like this scales quite well for electronic de-excitation on 1 monolayer. So the question is, what kind of lifetime increase can we expect if we go to 2 or 3 monolayers decoupling the spin from the substrate? And so to get a handle on the conductance of the substrate, we can do a point contact measurement between the STM tip and the iron atom on the surface. So at this point, we basically bring the tip into contact with the iron, so we no longer have the tunnel barrier on the tip side of the atom, and we're just measuring the tunneling through this MgO layer. And so we can do this on 1 and 2 and 3 monolayer, and notice that the tunnel current increases exponentially as we decrease the distance to the iron atom until it plateaus at some conductance value. And so we take this as an indication that 2 monolayers is 9 times more insulating than 1 monolayer. So what does that mean for the lifetime? Well, this rate of de-excitation goes as in the limit of low tip sample conductance. We're only interested in the intrinsic relaxation lifetime. This goes as a square of the conductance of the substrate. And so we expect that if a factor of 9 times more insulating substrate would give us a 81 times longer lifetime. So let's see what happens. So here's the lifetime at 5 Tesla for 1, 2, and 3 monolayers. And we see that we have, in each case, reached a plateau value where the lifetime has started to roll off from the tip induced decay. And I'd like to point out that this is pump probe taken at 50 femtoamps. So we're heading towards a teraohm of junction impedance just to actually characterize something intrinsic about the atom on the 3 monolayer MgO. And we can fit this with the electronic de-excitation model. And this is informed by the ratio of conductances of these at point contact that tells you the ratio of conductances of the substrates. And so that sets the spacing between these curves. And we can see for 2 and 3 monolayer that we expect these large increases in lifetime that we just don't get. And so we suspect that there's another mechanism at play here which limits the lifetime to about 15 milliseconds at 5 Tesla, and the best that we've seen is about 25 milliseconds at 2 Tesla. Okay, so yeah, we think we're running into some phonon limit that's somehow a property of this MgO layer, and we'll just get to something that won't scale anymore at some point soon. But if you want to go to junction impedances of greater than a tera ohm, that's great, because I don't. So, okay, we've discussed spin relaxation. So this is T1, the rate of energy relaxation from the spin to its surroundings. And knowing about T1 and about the tip height actually informs a lot about what we needed to know to be able to do this experiment, which is electron spin resonance. And so this now informs the T2 phase coherence time of this spin system. And we can also derive the principal parameters of spin resonance, namely not only T2, but also the driving strength. So let's dive on in. All right, can we do ESR on a single atom in an STM? And in particular, can we use radio frequency electric fields to drive it? So the idea of this would be if we have this the Zeeman split ground state with some delta E between them, can we tune the frequency of the electric field to match that splitting? And so we're typically dealing with 100 microvolts or 24 gigahertz, roughly. And so if we were to sweep the frequency of the electric field, and if this were to work, we would go from a thermally populated ground state. So essentially the excited state is very little populated at under thermal conditions. And then if we swept it over resonance, we would get an increase in the population of the excited state up to a point where the state was fully randomized to 50%. So this is a continuous wave ESR experiment. And so what that means for our spin polarized detection is that we measure a change in the DC tunnel current. So just as we did pump probe or the two-state noise switching, we also measure that DC conductance. So as a function of RF frequency, we'll be looking for a change in DC tunnel current. So let's take a look at these RF sweeps. So the idea here is to set a DC tunnel current set point of a picoamp. Okay.
Is like what makes the relation between the 0 and the 1 state possible?
I'll get to that. We're just saying what if at the moment. And then we'll see if this works first. Okay, so we put a picoamp DC tunnel current set point, and we apply a DC bias of 5 millivolts along with a constant amplitude oscillatory bias between 20 and 30 gigahertz. And we measure the essentially DC tunnel current as a function of this RF bias sweep. And so we see that at this particular field, we get one peak where the tunnel current changes by about 70 femtoamps from the 1 picoamp set point. And to check that this is a magnetic signal, we can change this energy splitting with the B field. So we can ramp the Z field and measure this as a function of field. And we see that the frequency of this peak moves linearly with applied field. And there's one peak between 20 and 30 gigahertz. Incidentally, we measure no peaks with a non-spin polarized tip. So the readout is really from the spin polarized tip. All right, so I'm claiming that we can manipulate the magnetic state of these atoms with electric fields. And that sounds weird because electric fields don't act on spins, but they do act on orbital moments. So to understand this, we need to look at the eigenstates of 0 and 1 in terms of their orbital and spin quantum numbers. So Suzanne already explained why this Hamiltonian is reasonable. And so we consider this Hamiltonian, which describes all of the symmetry allowed operators for the fourfold binding site of the MgO, and considering the 6d electrons in the Hund's rule ground state, S equals 2, L equals 2 of the iron atom. And the parameters of this Hamiltonian are D is minus 433 millivolts, and as Suzanne said, this brings the ML plus minus 2 terms lowest in energy, so we expect that the ground states will be composed of ML plus minus 2. And F0 sets the fourfold anisotropy of the system. And this actually leads to a transition. We can set this parameter based on a transition that we can see to 105 millivolts in spin excitation spectroscopy. And then the spin orbit coupling constant, along with F naught, give us the zero field splitting, which is the 14 millivolt IETS step. All right, so now the time-dependent electric field will act to pull on the atoms because they're all charged. And we believe that what's happening is we're modulating as a function of time these orbital parameters in the Hamiltonian. So the picture is that we're pulling on this atom resonantly, and this means that the orbital terms here are modulated as a function of time. So the question is, what's the coherent driving strength of this transition? And so it's given by the overlap of the ground state 0 and 1 under this operator L plus to the 4 plus L minus to the 4. Now this means that we need a delta ML is 4 and delta MS is 0 transition. And if we look at these states, so these are just the leading terms. There's a bunch of other things that are much, much smaller. If we look at these terms, we have this delta M equals 4 because we can go from plus 2 to minus 2 or minus 2 to plus 2. But the spins are essentially polarized, so we can't do delta MS equals 0. So this coherent driving strength is actually vanishingly small, or is quite small under normal conditions. But we can actually add a BX field, which mixes the spin states and gives us a much larger transition intensity. So in these experiments, we apply 5 to 7 Tesla in plane, and we have about a 2-degree tilt out of plane. So the BZ field is this small Zeeman field, whereas the BX is the thing that mixes the spin states and allows the coherent transitions. Okay, so we can look at some resonance lines now, and this is taken at low power. And at low power, a continuous wave ESR line is broadened by the phase coherence time T2. So as an estimate, we can take T2 to be 1 over pi delta F, and this gives us 100 nanoseconds. Of course, this might be power broadened. So we'll get to a better estimate now, which is a power saturation experiment. And in this experiment, we vary the power of the ESR drive and fit to the shape of the Lorentzian line peak. So the continuous wave ESR line shape is Lorentzian, and it has 3 parameters. Omega, which is the coherent drive strength, which is proportional to the RF voltage that we apply. T1, which is the energy relaxation time, which we talked about before. We obtain this independently from pump probe because you see it appears always next to omega, so you can't get them at the same time from this measurement. And then T2 is a phase coherence time. And so we obtain the ESR spectra at different RF amplitudes. And you can see that the full width starts out basically limited by T2, and we aren't getting down to that intrinsic width yet, but the fit of this is informed by also how the peak height changes. So the peak height starts increasing, and then eventually we get to a full randomization of the spin state, and this is where we get to 50-50 population. So this yields a phase coherence time of about 200 nanoseconds, and a Rabi flop time at our maximum RF voltage of about 1 microsecond. Okay, so one of the cool things about the STM is we can do this on different atoms, and we can look. So far I've shown you Beatrix down here, and we can also do this on Chris, Earl, Fred, and George. And these atoms are free of defects to about 1.5 nanometers. So there are a couple things around them, but there's no very close nearest neighbors. And we can see that they all vary linearly with field. And one of the interesting things is that there's about a 3 gigahertz spread in these things, which would actually lead you to a large inhomogeneous broadening if you did this as an ensemble measurement. Now, in this series, there's 2 missing. There's Andy. He died in an accident. and Daisy. And Daisy is actually up here. And the interesting thing about Daisy is Daisy has a neighbor, and that's a cobalt atom. So iron has a moment of 5.2 μb, and cobalt has a moment of 5.5 μb, and these are known from previous work. And these 2 atoms are 5 and 1 lattice spacing apart. That gives us 1.5 nanometers. And what we see is not only 1 resonance line on this iron atom, but 2. And these are shifted by 530 megahertz, which is 2.2 micro eV. This is a stunning energy resolution. We're actually limited to about 10 megahertz peak position, which is like 40 nano eV. And this is a 10,000 time improvement in energy resolution in the STM over temperature limited spectroscopy. So what's going on here is we actually measure 2 lines because this cobalt is actually flipping thermally, and its T1 time is shorter than the time that it takes to sweep across these spectra. And so when the cobalt is aligned with the field, its dipole field is actually making the local magnetic field on the iron smaller, and so we measure this lower line. And when the cobalt flips to its excited state, and you can see this peak is smaller, so it's populating it less often, then its dipole field adds to the splitting and makes the iron atom have this frequency up here. And this is also suggested that we could also continue to do quantum gates with this kind of thing, where we conditionally flip the iron based on the state of a neighboring atom. And we might also be able to use this iron atom on the surface as an atomically defined quantum sensor in a UHV clean environment on a surface. And maybe we can also use atom manipulation to place it nearby molecules and so on, and measure these couplings via the ESR line frequency. Okay, so to conclude, we've discussed the spin relaxation times that are intrinsic to the iron atom on the surface, where we've gone back in tip sample impedance well enough to see a plateau value. And we see that there's some limit beyond just electronic coupling to the substrate. And the T1s are very long, and they're long enough for you to see in real time on an oscilloscope. And then we've discussed spin resonance, where we have the time-dependent electric field, which modulates a Ligon field, which can do these transitions. And we've determined the principal parameters of the ESR, so a phase coherence time of 200 nanoseconds and a flop time of a microsecond. And we are really looking forward to applying this to quantum sensing and computation with atoms on surfaces. So I'd like to thank the great team that I get to work with at IBM of Andreas, Chris, Suzanne, Taeyang, Kai, and Bruce. And we've had a lot of great visiting students. And this has been supported by theory work at IBM. Arjang at Oxford has been a great inspiration for electric field-driven ESR. And we've had a lot of help from these guys in Switzerland to actually understand the magnetic states of the atoms. So thank you very much.